Welcome to section 2.2, polynomial functions of higher degree. By higher degree, they're referring to beyond just quadratics, which was the topic of 2.1. So let's get started. Things that are synonymous or basically equivalent statements. If we have a polynomial and a is a zero of the function, so if x equals a is a zero of the function, so somewhere along here we have a polynomial. Right here, a is a zero. Let's say this is the x value of a, where a to the right. So a is a zero. That means that x equals a is a solution if we set the polynomial equal to zero. Somewhat goes without saying. X minus a, therefore, is a factor of the polynomial. And a0, as we can clearly see, is an x-intercept. This is probably, they're all, I think, somewhat obvious after we get comfortable in this environment, but this one becomes particularly important to us. X minus a is a factor. If a is an intercept, or a is a zero, or a is a solution to the polynomial f of x equals 0, then we may factor out x minus a. That becomes a huge part of what we're going to be doing. Excuse me. Okay, lead coefficient test. If you've taken this course with me or seen previous videos, this is pretty well explained when we went through sprinters, intermediate runners, distance runners. And what that says, if I have a polynomial such as, let's say, negative x to the fourth minus 3x cubed plus 2x minus 5. So y equals, or f of x equals. What the lead coefficient test means is if we take the term of the polynomial with biggest degree, in this case 4, and we look at the lead coefficient here, for instance, is -1. So when n, our exponent, is odd, well, this one's even. So n is even, then we either have a right side up quartic or fourth degree polynomial, or an upside down. If it's right side up, we would say it rises to the right and rises to the left. We don't say it falls from the left. Technically they're the same, but nomenclature, we just should be calling this rises to the right, rises to the left, versus if the lead coefficient is negative, which is our case, it's going to fall to the left and eventually fall to the right. Now it may wiggle through the middle, but eventually its end model behavior doesn't matter what's behind this information up here. A negative even is going to fall to the right, or fall to the left. Whereas this is a negative odd. Doesn't matter that it's wiggling. If the lead coefficient is negative, polynomials are going to fall to the left. If it's odd, they go in opposite directions, eventually right and left. So this is a positive odd, positive even, negative odd. So we can tell a lot about, see, that's our distance runner. This term is in control eventually. Eventually this wants to look like negative x to the fourth. It's going to fall to the right, fall to the left. Okay, repeated zeros. We say multiplicity. For instance, if I have y equals x minus 2 squared times x plus 3, 2 is said to be a zero of multiplicity 2. It's a double zero. Okay. If k is odd, if it's an odd degree, 0, in this case we're even, then the graph crosses through the axis. Not only does it cross through, but it flattens out. We'll talk about that, provided k is greater than 1. If k is even, then it's just a touch. So our graph, the graph of this at 2 is just going to touch. Now it may go up, may go down, maybe we're not certain. I do know there's another 0 here at -3. And I know if I superfoiled all of this out, I'd have positive x to the third. So eventually it's going up to the right. Eventually it's going down to the left. It must cross here, and this is just a touch point. So really gives us a good idea of the shape of the graph if we understand those things. Now, we probably won't talk a whole lot about intermediate value theorem. It's really a simple idea, and I'll go through it here, but it becomes really important in calculus. So here's what it says. Let A and B be real numbers such that A is less than B. And we're going to think of that as, since they're talking about an interval AB, A is to the left of B. If f is a polynomial function such that f of A, the height at A, does not equal the height at B. Let's just use this for example. Let's say this is over A, and let's say this is B. A is to the left of B, the heights are not equal, then what it says is in the interval from A to B, f takes on every value between the height of A and the height of B. So here's the height of A, the height of B. All the values, let's say y-axis was right here, all the values from here to here get hit along the way. As we can see, it happens right in there. All that really means is that to get from here to here, if I'm on a polynomial, I don't pick the pen up to draw it. So I have to hit all the values between. I didn't have to go down here. I could add a polynomial that looked like this, but we hit all the y values between here and there. Like I said, not something we're going to talk about a whole lot in this course, but a really big deal in calculus. Okay, now 9 through 16, some of my favorite problems in this chapter, and we actually know a whole lot more about the graphs of these than what we need to answer this. To answer this question, all I really need to do for my matching, to match with these formulas down below, is recognize this is probably third degree, and it's positive. And that's probably enough for us to eliminate and know which answer we have from 9 through 16. However, what else do we know? This is going through y-intercept of 1, so at the very end of this, there's a plus 1. It's going through that temporarily like a line with negative slope. I have negative something, maybe ax. Negative some value or minus some positive value x, because it looks like a negative line for an instant. And then eventually it's going to act like a positive cubic. So I have a positive cubic out in front. Maybe there's a little squared term in here, but I have all of those things going on with this. So I look for my cubic, my positive cubic. Here's a positive cubic with a negative linear component that's up 1. So I'd like to have you take the time to look through all of those things, because we can narrow this down. If you note, this is the only positive cubic to choose from. Whereas this is rising to the right, falling to the left, negative cubic. Appears as though it's going through 0 with a positive line. So goes through 0 with a positive linear, maybe just 1x, but I'm just going to say ax. Next thing, it looks like temporarily after that, as we open up the door, it starts to look like a negative cubic. There's probably a negative x cubed in here, and probably a positive x to the 5th at the end of it. Let's take a look. Positive x to the 5th, negative cubic, positive linear. Whoop, here it is, sorry. Positive to the 5th, negative cubic, positive linear. So number 12, let's see, that was our A. Number 16 is our B. Got that one done. This is an upside down parabola. Not only is it an upside down parabola, but it's an upside down parabola that's going through 0 and temporarily looks like a negative line going through that. I need negative cubic, negative line, no constant. So I'm looking for something like a negative x cubed and, negative x squared, and something with a negative something x, but no constant term. So where do we have it? Here's a negative parabola, negative quadratic, negative line. Number 11 is C. Great problems. So again, knowing this is likely a negative cubic might be enough, but I know this negative cubic, it appears to be down 1. It appears to immediately then be flat at that instant and start looking like a positive parabola. So positive parabola, it must have something like an x squared term in before it becomes a negative cubic. So let's find our negative cubic. Here's a negative cubic with a positive parabola, and it's down, whoop, I guess it was down beyond 1, down past that. Well, there's a 1 marker. It looks like it would be down a little bit further than that. Okay. E, probably a negative to the 4th graph, but it goes through 0. It immediately then looks like a positive parabola. The next change it makes is it starts to look like that negative to the 4th. Positive parabola. So I'm looking for my positive to the 4th. It's not that one. I'm looking for another positive to the 4th. Or excuse me, negative to the 4th. I said negative to the 4th. Here's a negative to the 4th with a positive parabola. E. Did we come up with D? Yeah, we got D already. Okay, F. F is, of course, is just a line, negative slope, up appears to be up 3. So this is F. G. Can't be a parabola because there's some wiggling. It's more than a parabola. It rises right and left, probably to the 4th. It looks like 0 here, goes through 0. It looks like it's flat for an instant, so that would be 0x. It then looks like a positive cubic before it looks like a negative to the 4th. And there's our, or excuse me, positive to the 4th. Positive cubic, positive to the 4th, no x's, no x squareds. So there we go. We've got G. And H, positive parabola, goes through 0, but going down through 0. So it's like a plus 0. It's got a negative x term with some coefficient in front of there before it becomes a positive x squared. X squared minus 4x. There's our H, and this one was our F. Okay. So again, that's maybe a little overkill just for getting the assignment done, but I can't begin to express how important that concept or those concepts are for your future in this course, and truthfully throughout all of your math courses, through all of your calculus series. Okay, in exercise 17 through 22, sketch the graph of f equals x cubed and the graph of the function g. Describe the transformation from f to g. So the graph of x cubed is just 0 gives me 0, 1 gives me 1, 2 gives me 1, 2, 3, 4, 5, 6, 7, 8. By the time I'm at 2 on x cubed, I'm up there. So I'm just going to sketch that in lightly. Negative 1 gives me negative 1, negative 2 gets me down to negative 8. That's a parent function, one we're familiar with. So g should look just like that, except it's down, excuse me, right 2, my vox is 2, and down 3. So right 2, down 3. Now, from that point, I could take this point right here, right 2, down 3, or I could say this is growing just like a regular old cubic. And regular old cubics want to go to the right one, up 1, want to go from the, I'm not going to call it vertex, but maybe from the center, from the most interesting value of x, to the right 2, up 8, 3, 4, 5, 6, 7, 8. Notice that's right 2, down 3. They want to go to the left 1, down 1, and they'd want to go to the left 2, down 8. This graph, 21, wants to look just like x cubed. Get it over here in the light a little bit more. Wants to look just like x cubed, which starts right here, but it wants to be to the right 3 and post function upside down, but upside down stays there. From there, regular old cubic would go right 1, up 1, but this one is upside down. Right 1, down 1. would want to go right 2, down 8, or left 1, up 1, left 2, up 8. Now, one thing worth noting, when these things get to their most level point, they truly are completely leveled out. Okay, good stuff. One of my favorite sections. In exercise 23 to 28, use a graphing calculator to graph functions f and g in the same window. Zoom out on these. So let's go ahead and take a look at what they're trying to, the point they're trying to get across. Hopefully you're already aware of the point they're trying to get across. But we will take a look at this, and I'm going to go my graphing calculator, clear out this first function, and we have 3x to the 4th minus 6x squared. Second function, just 3x to the 4th. And I'm going to go ahead and graph that in Zoom Standard, Zoom 6. Here's our first more complicated function. And our second function. So there's some similarities. It says zoom out far enough to see the right hand and left hand behavior of each graph. Well, it seems to me the right hand and left hand behavior of each graph is both graphs are going to rise to the right and fall to the left. Do the graphs, do they have the same right and left hand then behavior? Explain why or why not. Well, the lead coefficient in both cases is positive, not only positive but positive 3, and they're both even degree. They're both 4th degree. Therefore, they're the same. What I want to do with this one, I'm going to just do a zoom fit on this because I know the values are getting big fast. So I'm going to go zoom 0, which is zoom fit. Here's our first function. And our second function, not only do they have the same end model behavior, rise to the right, rise to the left, if we zoom out far enough, they basically look like the same function. Okay, so yes, they have the same, I'm not going to write it down, but they do have the same end model behavior, and that is because they are both positive and even. Okay, 29 through 36. Use the lead coefficient test to describe the right hand and left hand behavior of the graph of the polynomial. Well, don't get trapped here. This is not a positive cubic because if we distributed, we would get negative 7/8 s to the 3rd dot dot dot. And the dot dot dot's pretty insignificant here because all we're talking about is end model behavior. They call it right and left hand behavior, and that's fine. Here at Hananiga, we talk about end model behavior. You need to be familiar. They're both the same thing. Both times we're going to use the preposition to, not from. So this is a negative cubic. Eventually, it can wiggle around in here. In fact, I could do this. I could say, well, it's going to start around, distribute this, negative 7/8. Doesn't really matter for this problem. It's eventually, this would be positive, going up through there, and then it's trying to curve like an upward parabola, downward parabola because I distribute the negative, but eventually it's going to look like a downward cubic. It's going to look like this, but we don't really need the graph to know that because it's just negative and odd. Therefore, it rises to the left. As we go to the left, it's going up, and it falls to the right. And you're certainly welcome to check that with your graphing calculator. Okay, 37 through 48. Find the zeros algebraically. I'm going to factor this. 5x squared minus 2x minus 1 equals 0. Quick distribute, check it. 5x squared minus 10x minus 5 equals 0. And now to find those zeros, I can divide both sides by 5. I'm left with x squared minus 2x minus 1 equals 0. Are there factors of -2 that, or -1 that add up to be -2? There are not, so I could go quadratic formula, or I could try to complete the square. I'm going to go quadratic formula. X equals the opposite of b, 2, plus or minus root 2 squared, -2 squared 4, b squared 4, minus 4 times a times c. Minus 4 times 1 times -1, that's minus -4, all on 2a2. That is 2 plus or minus root 8 all on 2, and this is a real sad thing I see happen in this course with some of our best algebra students we have. Really tempting to cancel the 2's. I may not at this time because 2 is not a factor. But I can change square root of 8, make this square root of 4 times 2, square root of 4, 2 root 2 divided by 2. And now I can cancel top and bottom with 2's, and I get 1 plus or minus, I divide both terms by 2, square root of 2 all on 1. So there's my zeros algebraically. You can check those on calculator. You can use the graph to approximate any. We could go through that process. I'm going to go through that with this one problem only with you. I'm not going to repeat this for 42 and 48 because it's a little bit redundant. So I'm going to go into y equals, clear out the second graph. First graph started out as 5x squared. Clear this. Sorry. Try that again. 5x squared minus 10x minus 1. And I'm going to zoom standard. And what I'd like to do is find the zeros of this parabola. So second calc 0. I'm going to get to the left of that 0, enter. To the right of that 0, enter. Take a guess, and it says x is -0.095. And then I'm going to second calc the other 0. Get to the left of it, enter. Right of it, enter. Guess, enter 2.095. I'll put it down here, 2.095. And I'm just going to do a real quick check here. Let's go 1 plus square root of 2. There's my 2.41. Yikes, we got some issues here. So let me go back in and double check this, making me a little bit nervous. I don't really want to start this video over, so let's go back in and check. Did I enter this correctly? -5. I'll bet you saw it and were yelling at the screen. Okay, maybe that's why we check things, but I think my error was on my second part. So let's go again and graph this. I'm going to calculate just the 0 on the right. Second calc 0. I'm going to get the one on the right. Enter. Enter. 2.141. Mistake back here. 2.141. I'm going to second quit. Check that value. There's my 2.141, and I'm going to suggest that the second would work as well. Apologies for that entry error. Okay, most concerned in the algebra on this. So let's find the zeros algebraically. So I'm going to factor out a t. T times t to the 4th minus 6t squared plus 9 equals 0. This is not quadratic because it's to the 4th, but it is quadratic on t squared. It's not quadratic on t because I've got 2t squareds, a t squared, and no t squared. So perhaps this factors again. Are there factors of 9 that add up to -6, -3, and -3? t squared minus 3, t squared minus 3. If that equals 0, then t equals 0, or t equals plus or minus root 3, or t equals plus or minus root 3. So find the zeros algebraically, use a graphing calculator. So my zeros are t equals 0, t equals root 3, and that is a multiplicity 2, and they don't ask for that, but I'm going to show you what that means. And also t equals negative root 3, that's a multiplicity 2. Both of those are double zeros, so I am actually going to graph this one just to show you this, and I'm going to do it right the first time here so as not to waste our time. So let me get down here, clear this, and let's go with, got my function, yep, x to the 5th minus 6x to the 3rd plus 9x. And I think I'm in standard, but I'm going to zoom 0, zoom standard that. Nope, I just zoom fit it. Mistake. I'm going to regret that a little bit. Zoom 6, zoom standard. I want to see those zeros nicely defined. And here's what we're seeing. It looks like we have a 0 that goes right through 0. But it looks like we have a touch over here just to the left of 2. I'm going to look at that one. Second calc 0. I'm going to get to the left of maybe that 0 there, which I think actually is a 0. I'm going to get to the right of it. And I'm going to hit enter. And if you look at this 1.732, I'm going to suggest, and you can check it, maybe you recognize it, that is square root of 3. And over here we have a double 0. So this is what's cool, because it's a double 0, because these popped up twice, it really acts like a second degree. It acts like a parabola at those points. I have another discussion where I talk about, I have an analogy where I call it husband, wife, brother-in-law, and kind of an interesting perspective on why these look the way they do. This 0 is a single 0, and it looks just like a line going through there. Okay, let's take you through 48, and then we're going to pause this and come back with a part 2 to this one. Very similar. I'd really highly recommend you going ahead and pausing this right now and try this one. I'll be back as soon as you hit play. Okay, hopefully you tried this and you've gotten through it. I'm going to set this equal to 0, factor out an x. I get x to the 4th minus 5x squared plus 4. For that to equal 0, I'm going to go ahead and factor. Again, this is not a quadratic on x, but it is a quadratic on x squared. Are there factors of positive 4 that add up to negative 5, negative 4, and negative 1? So I get x squared minus 4 and x squared minus 1. And a quick FOIL, let's check it. Here I get x to the 4th minus an x squared minus 4x squared's got it, and a plus 4. And those further factor difference of perfect squares, x plus 2, x minus 2, x plus 1, x minus 1, and therefore my zeros are x equals 0, plus or minus 2, and plus or minus 1. Now, if I just wanted to know what the graph looks like on that, 0, 1, 2, negative 1, negative 2, I'd have a 0 here, a single 0 here, a single 0 here, a single 0 here, and a single 0 here. What's the graph eventually do? End model behavior, positive to the 5th wants to look like that. So eventually, I'm doing this. These are all single pass-through me zeros, single zeros. So pass through me, pass through me, pass through me, pass through me, and pass through me. How high do they go in there? I'm not certain. I'd have to pick some values and check. Okay, pretty good pausing point. We're at the 30-minute mark of this video. So I will come back with a part 2 shortly. Before I do that, probably a good time if you're working at home for me to show you the assignment set. This would include the part 2 that we're going to handle on the next video. So you may pause that, take a picture of that, do what you want. There's our assignment set.